You can't take 3 from 2. 2 is less than 3, so you look at the 4 in the 8's place. Now that's really 4 8s, so you make a 3 8s, regroup, and you change an 8 to 8 1s, and you add to the 2, and you get 1 2 base 8, which is 10 base 10, and you take away 3, that's 7. Okay? Now instead of 4 in the 8's place, you...
Things to know. Before you want to tackle related rates problems, you should understand differentiation, the chain rule, and implicit differentiation.
Air is being pumped into a spherical balloon at a rate of 4.5 cubic inches per minute. Find the rate of change of the radius when the radius is 2 inches. Alright, so this is a typical related rates problem. So they want you to find the rate of change of the radius at a specific time when the radius is 2 inches. Okay. So here's the formula for finding the volume of a balloon or a sphere. In this case, it's a spherical balloon. Now, if this were an algebra class, they would ask you to find the volume at a given radius, or maybe the radius at a given volume. But since this is calculus, we want to find out the rate of change of the volume, or the radius. So, let's go ahead. Now, if we differentiate this with respect to time, we'll get dv dt equal to... Now, 4/3 and pi are just constants, so I'll just leave them there. And then, we differentiate this using the power rule. So, times 3r squared. But remember, since we're differentiating with respect to t, we can assume r to be a function of time. Therefore, we have to use the chain rule. And then we'll also get times dr dt. Now that we've got our equation, well, we could simplify this a bit. Get rid of this 3 here. I'd end up with 4 pi r squared dr dt. Right? Now let's go back to the problem. Air is being pumped into a spherical balloon at a rate of 4.5 cubic inches per minute. Now, this gives us dv dt. Okay? The rate of change at which the volume is changing. So, dv dt equal to 4.5. Find the rate of change of the radius, so we're finding dr dt, when the radius is 2 inches. So then, r equals 2. Now that we've got our given, we can simply plug it back into the differential equation we got. So, dv dt 4.5 is equal to 4 pi r squared 2 squared dr dt. At this point, we would just use algebra to find dr dt. So 4.5 is equal to 16 pi dr dt. Alright, so dr dt is equal to 4.5 over 16 pi. And of course, I can't do that mentally, so I'm going to enlist the aid of the calculator. 4.5 divided by 16 pi. And it is approximately equal to 0.884. Inches. Now, always remember the units. Okay? In this case, it's given that it was inches, and since the rate of change of the volume was in cubic inches per minute, it's over minutes as well. Now, does this answer make sense? Let's see. Air is being pumped into a spherical balloon. That means the volume is increasing, therefore the radius should increase as well. Therefore, it can't be a negative answer. Okay.
Water is draining from a conical tank with the height of 12 feet and a diameter of 8 feet. The depth in feet of the water in the conical tank is changing at a rate of h minus 12 feet per minute. At what rate is the volume of water in the conical tank changing when h equals 3? Okay, so looking back at the problem, we are looking for the volume in the conical tank, but this time we're finding the rate of change of the volume. So we'll have to use implicit differentiation. So when the derivative of V is the rate of change of volume with respect to time. And so 1/3 pi is a constant, so we're going to isolate that over here. And now we have radius and height, which is two variables. So we're going to use the product rule, and since it's r squared, we're going to have to use the chain rule. So r squared, and the derivative of height is dh over dt. And we're going to add h, and now we're going to differentiate r squared, so 2r dr over dt. So let's look back at the problem for what we're trying to calculate. So we want the rate of the volume of water in the conical tank. So that's good because we already have the rate of change of volume of the conical tank on this side. So all we have to do is find the values of the variables. So we have the depth in feet of the water is changing at a rate of h minus 12. So that is dh over dt. So we have that. And we're trying to find it when it's at h equals 3. So we have h and dh over dt. So what we have left is dr over dt and the radius. So there's the problem, but we could figure that out if we drew, well, it helps to draw. We're going to use this to find r and dr over dt. We are going to put r in terms of h, so we could plug it in. So this is where proportionality comes in. Okay, so here's our proportion, and where did I get these? This is the radius of the cone, and the radius of the water, and the height of the cone, and the height of, the height of the water. So what we're going to do to get r is to cross multiply. So r equals 4h over 12, which you simplify to h over 3. So to get dr over dt, you just differentiate. So dr over dt equals 1/3 dh over dt. So now we have r and dr over dt. So we're ready to go to plug stuff in to the equation. So we're going to start plugging things in. So 1/3 pi, r squared is h over 3, so h over 3 squared, and dh over dt, remember, is h minus 12, plus h. We're just going to put these in terms of h, so 2 times r again, which is h over 3, and dr over dt is 1/3 dh over dt. And 1/3 and dh over dt, which is h minus 12. So h minus 12. So now everything's in terms of h, and since we know that h equals 3, we can start plugging in the 3's. So 1/3 pi, 3 over 3 is 1, 1 squared is 1, 3 minus 12, negative 9, plus 3 times 2 times 3 over 3, which is 2, times 1/3 times negative 9. So we can simplify this. 3 pi, negative 9. So we cancel out the 3, so it's 2 times negative 9, which is minus 18. So this is 1/3 pi times negative 27. And so the final answer is negative 9 pi. Since its rate of change in volume, it's feet cubed per minute.
Alright, some tips for related ridge problems. The first step usually is to draw a diagram. It helps you visualize and it keeps you organized. Okay. The second step is to assign variables to each quantity in the problem as a function of time. You have to remember that with every variable, even the radius, when you differentiate it, it's respect to time. 3. List all given information and rate of change to be found. Again, it keeps you organized, it tells you what you know and what you want to find. And lastly, 4. Write an equation relating the variables. Usually this is given in the problem, but if it isn't, then usually it's a geometric formula.